Thanks again for joining us for this webinar. My name is Mike Raley. I am PAC's Director of Engineering. I'll be giving the presentation today. So this presentation does count for AIA credits. And so, make sure you stay here and you've registered through AEC, that registration link, to make sure that you get your credits. Today's presentation, the topic is better design through a deeper understanding of acoustic ratings. So I'm going to talk about the STC and the IIC ratings, two common ratings you've probably heard about. And we have a sort of a wide variety of folks here today. We've got quite a few architects. I think we've got some contractors and folks here, and also a fair number of acoustical consultants. So there's probably some of you on this call who know these STC and IIC ratings far better than I do. But I'll go ahead and talk about them. Hopefully there's some useful information for y'all as well. And I'm also going to talk about two new, fairly new acoustical standards that have come out in the past couple years or so. And those are the HIIC and LIIC standards. I'm going to talk about how those are useful, what they do for us, what they are. So with that, I'll go ahead and get into it. Right, it's just an overview of what I'm going to talk about. So I'm going to talk about the STC and IIC ratings and what are they. I'm going to talk about the difference between lab and field measurements. This is something that comes up. You see it referenced in the building code for acoustical standards for sound isolation in large residential buildings. I'm going to talk about what those differences are. Talk about some myths and misconceptions, things that I've heard, questions that I've gotten a lot over the years. Talk about some of those and how they can lead us astray sometimes. Then I'm going to get a little bit more technical. I'm going to talk about reading the STC and IIC graphs because these single number ratings, the STC and the IIC, they don't tell us the whole story. Right. And so having a little bit better understanding of what goes into those ratings, I think can help all of us better design quieter spaces. I'm going to talk about how they're calculated and some of the shortcomings of them. Right. And then that will lead us into talking about these new ratings, the HIIC and the LIIC, and how they sort of address some of the shortcomings of the IIC rating. And then last but not least, I'm going to talk about methods of improving these ratings, just some sort of general concepts that you can use to apply and how they affect these different ratings. So before we get into this, I just kind of want to sort of set the stage for all of this, talking about these acoustic ratings and code minimums and everything with this quote. With the current level of performance specified by the building code, a large percentage of people are highly annoyed by noises from their neighbors, leading to reduced quality of life and possibly to negative health effects. Right? That negative health effects is a big thing, right? If we're trying to design spaces that are healthy, trying to design healthy indoor environments, right? Noise is a big part of that, and noise can really contribute to our health in a negative way. And so, this quote about the code and it not being high enough, this isn't some, just acoustical consultant saying, hey, everybody needs to do better, pay more attention to noise. This is actually from the International Code Council themselves. This is a supplementary document of theirs, the 2010 Guidelines for Acoustics. And it's a great reference. I've used it as an acoustical consultant as a reference, and I think it's also a great reference for architects and others to look at. So with that, let's get into it and kind of start talking about what these different ratings are and what the difference is between STC and IIC ratings. So first off, STC stands for Sound Transmission Class, and it measures the reduction of airborne sounds. So that's really sounds that start within the air. So we can talk about examples of people talking, TVs, stereos, those sorts of things. And STC ratings apply to both walls and floor ceiling assemblies. You can also have STC ratings for doors, windows, things like that, right? And the way we measure an STC rating is, I've kind of got this very simple sort of schematic layout of a laboratory setup, right? Is we have these two separate spaces, two isolated spaces. We have a sound source in one room. You can see the speaker up there in the upper left corner. We make a bunch of really loud noise in that room. And we'll measure how loud it is in the source room, and then we'll measure how loud it is in the receiving room. And basically the difference between those two, plus some other calculations and things that I'll go into, gives you your STC rating. So it's really just the reduction in noise from this space to this space because of this partition that you put in the middle. IIC stands for impact insulation class, and it measures the reduction of structure-borne sound. So we're talking about sound where it really starts with an interaction with the structure itself. And the IIC ratings only apply to floor ceiling assemblies. And some noise source examples would be footsteps, dragged chairs, dropped objects, your dog running across the floor, their nails on it, my kids jumping up and down, those kinds of things, right? And so we kind of see that illustrated here by this boot on top of the floor ceiling assembly with, somebody in their home office below, right? So the way we actually measure this in the lab is we have a standardized impact source called the tapping machine, and it has these little metal weights on it, and there's either like a cam or sometimes electromagnets that lift those weights up, and then they just free fall. And so you get this tap, 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 tap on the floor, and you just measure how loud it is down below. And you take that measurement of how loud it is below, you do this curve fit thing that I'll show you, and that's how you get an IIC rating. So the laboratory ratings, right? For airborne sound, we have the STC, and for impact sound, we have the IIC. And in the laboratory, we go to great lengths, hopefully, to isolate the two spaces, the source space and the receiving space, so that the dominant transmission path for the sound is through whatever assembly it is that we're trying to evaluate. So when we're doing the measurements in the receiving room, all of the sound that we're really capturing, measuring, is coming through that partition, not through other places in the structure. And so we call those other ways that the sound can travel around our main assembly, those are flanking paths. So we try to control or eliminate as much as possible those flanking paths. So therefore, we're only measuring the sound going through the assembly that we're trying to test. So then the results of that indicate the performance of that assembly independent of the surroundings. In the field, we have different ratings, and we have this whole alphabet soup, right? So for airborne sound, we have sort of three different ratings: an ASTC, an NNIC, and an NIC. And I'm not going to go into the differences between all of those and what they mean. Just when you see those, know that they are airborne sound and they're field measurements. And the differences between them really deal with room conditions, sizes of rooms, sizes of partitions, the amount of absorption in the spaces, and those kinds of things. Impact sound, we also have three different metrics. We have AIIC, NISR, and ISR. And again, very similar measurement methodologies. The differences is really just in sort of room conditions, site conditions, those kinds of things. So when we do these field measurements, the flanking paths are included in the measurements. So it's measuring the sound through all of the different paths, right, through our assembly, but also through, side walls and ducts and, whatever might be going on in our space. So we have the direct sound shown by these sort of teal arrows. And everything's connected, right? In the lab, we sort of isolate these spaces so that they're not connected to each other. But in the real world, everything's structurally connected. So we have all of these other paths. So for a floor ceiling test, we've got the direct sound through the floor ceiling, but we also have sound that could be transmitted through the walls and down into the space below, or even down to the floor and up from that. And there's a whole bunch of different ways that the sound can go. So the results of a field test indicate the performance of the assembly and the surrounding structure. And what that means is that the results are applicable only to the tested assembly. And if you look at the ASTM test standards for these field tests, they say, like, if you do this test, it's only applicable to this exact situation, because even if you moved somewhere else in the building, you might have different circumstances in terms of how the walls are built. Maybe the units are stacked in one place and they're not stacked in another, and you have all of these different sort of connections and things like that that affect your flanking paths and are going to therefore give you different results. So those are sort of the differences between the lab and the field tests and sort of how we conduct those lab tests. So then the code requirements, right? Within the International Building Code, we have requirements for airborne sound, right? And for structure-borne sound. And the laboratory requirement is a 50. So if you're looking at a laboratory test report, it's got to be at least above a 50. And for field, it's a 45. And that's the same for both airborne and structure-borne sound. And if you're designing, if you're looking at a space for multifamily, apartments, condos, anything like that, you need to meet both the airborne and structure-borne sound isolation requirements. All right, so now let's get into some of the sort of myths and misconceptions. So the first thing is you can add STC ratings. Like I've had people ask me about this before. Hey, I've got this assembly that's this base assembly that's an STC 35, and then I've got this other thing that tested at a STC 20. Can I just add the two together and get an STC 55? I wish that it were that easy, but unfortunately it's not. So I have an example here. This is standard 2x10 solid wood joist, some bad insulation in the cavity. And in this particular test, there's just a wood subfloor. It was OSB or plywood, and nothing on the ceiling, right? So the joist cavities were exposed to below. And that got an STC 24. And then we kind of take the flip side of this, and we have something where the top side is exposed, and we just have a ceiling. So this is resilient channels and a layer of gypsum board, and that got an STC 27. So can we just add the two, STC 24 plus 27, and get a 51? Hey, this assembly meets our code minimum of 50, right? Well, unfortunately, if you actually just go and test that assembly, you get an STC 49. Now, it's not a huge difference, right? 2 points is not that big of a deal. And I could come up with other examples where you do this sort of addition of different elements of an assembly and you come up with much bigger differences. But I used this one to show how this could, if you tried to do it this way, it could get you into trouble, because just adding the two STC ratings shows, hey, yeah, this thing's going to be above the code minimum of 50. But in actuality, if you tested the assembly as a whole, it's below. And so it's right at that break point. So unfortunately, you just can't add those. You really need something that tests the assembly as a whole, or you need to do a more detailed analysis of what adding or changing these different elements does. So another one that I get a lot is you can add a delta IIC to any assembly. So first off, what's a delta IIC? So we talked about the IIC rating, that's your impact sound, right? So we have the tapping machine, we have a floor ceiling assembly, and then we measure how loud it is down below. The delta IIC test standard specifies, okay, let's take a 6-inch concrete slab, and we're gonna measure our IIC rating on that bare 6-inch concrete slab. So we're gonna tap on it, measure how loud it is down below. And then take the same 6-inch slab and put some flooring on top of it. It might be tile on a rubber underlayment, it might be an LVT or engineered wood with an attached pad, whatever, put flooring on top of it, and then measure the IIC again. And the delta IIC is basically the difference between those two. So it's the improvement that you get from putting flooring on top of a 6-inch concrete slab. So here we have a delta IIC. I think that this is like engineered wood on a 2mm recycled rubber underlayment. And then here we have an assembly, and this already has a pretty high IIC rating. It's got gypsum concrete on an acoustical underlayment. It's got rubber sound isolation clips on the bottom. So can we just take these two, add a delta IIC of 24 to the 62 for the open web truss, and get an IIC 86? That'd be really awesome. But it doesn't work that way. Instead, you get an IIC 68 when you go and you actually test this assembly. And so the thing is, the delta IIC is measured always on a concrete slab. And concrete slabs behave very differently acoustically than do wood open web trusses or wood I joists or steel C joists or any of these other kinds of things, right? So you can't just take a delta IIC and add it to any sort of joist or truss structure. You can add it, it's measured on a 6-inch concrete slab. You could definitely do it for a bare 6-inch slab, and it'll probably work for an 8-inch or 5-inch, 7-inch kind of slabs. You get pretty close. Sort of heavy monolithic structures, but these lightweight joist and truss structures, it doesn't work. Another question that I get a lot is, hey, what's the STC rating for your clips, or what's the IIC rating for this underlayment? The acoustical products themselves, like the ones that are designed to be a part of an assembly, like sound isolation clips, acoustical underlayments, these kinds of things, they don't have their own STC and IIC ratings, because when we do those tests, we're evaluating the assembly as a whole, not the individual elements of it, right? We're producing sound on this one space, and then we're measuring how loud it is in the space below, right? And we have to have something that fills that whole opening between those two rooms in order to run that test. So here we have two different assemblies, the sound isolation clip in them, right? This thing right here is the same for both, but we have two totally different ratings. We have an STC 56 on the left and a 62 on the right. And the difference is just the number of gypsum board layers, but it's the same sound isolation clip and installed in the same way. So the clip itself doesn't have an STC rating. You have to look at the assembly as a whole. All right, so that's kind of the basic overview of the ratings, how they're measured, how we get them, and some of the sort of caveats, pitfalls, myths, and misconceptions around them. So now I'm going to get a little bit deeper, and I'm going to get into actually reading the graphs that you would get in a test report. So if you're, reviewing submittals from a manufacturer, something like that, you're getting acoustical test reports, laboratory test reports. In that, there should be a graph that shows this detailed data, one that kind of looks like what I have here on the right. And that will tell you a lot more information about the performance of the assembly if you sort of understand how to read it. That's what I'm going to go into now. So yeah, the graphs give details of the assembly's performance beyond just the single number STC and IIC ratings. So ISPL stands for impact sound pressure level. It's measured in decibels, and it represents how loud are the impacts in the space below the assembly. So this is for an IIC test, or the field versions, AIIC, all of those things, right? For impact sound, structure-borne sound. TL stands for transmission loss. It's also measured in decibels, and it represents how much does the assembly reduce the noise levels from one side to the other. So it's for airborne sound. On the bottom here, the x-axis, the horizontal axis, we have frequency, which is in hertz. And lower numbers on the left-hand side of the axis are low frequencies. I'm a musician, so I always like to give musical examples. So you can think of lower frequencies as bass, upright bass, bass guitar, right? And the higher numbers are higher frequencies. So you can think of a violin, right? Or another example would be low frequencies would be the rumble of a diesel train engine. And high frequencies would be like the piercing sort of squeal of a fire alarm like this. And that fire alarm, just for reference, like the sort of standard for that I found is at 3,150 hertz, which is the upper range of the IIC frequency range we look at. And you can think of these frequencies along that horizontal axis or the x-axis as sort of like keys on a piano, right? On a piano, each key is a different note, and each note basically is a different frequency. It's a little more complicated than that, I recognize, for all of you acousticians on here, but you can basically think about these different frequencies as sort of different notes, different pitches. And bonus points to any of you for identifying the issue with this piano. All right, so the STC and IIC calculation. How do you actually get from these TL or ISPL values a single number? And it's kind of a weird and complicated procedure. It's a little confusing. So hopefully these two little sort of moving things here, animations, that show you how it's calculated, and hopefully this sort of helps understand. So on each of these, we have the actual measured data for the assembly that's here in gray, these gray lines with the dots. So on the left, we have STC, and that's airborne sound. And on the right, we have IIC, that's impact sound. So we start with our measured data that we've gotten from the laboratory or from the field. And then we have this orange curve, which is set within the calculation standards that are developed by ASTM. And we do a curve fit. So basically, we shift this orange curve up and down, and we look at the differences between that curve and the measured values, the gray line. And so for STC calculation, higher transmission loss values are better, right? Because it's more noise reduction, and we want more noise reduction. So anything that's below the orange line, we call a deficiency. And really all that means is that it's just less than this curve. And so you can see in this animation on the left, as we raise the curve up, on the bottom, we get these little bars, and those are the deficiencies. On the right, for an IIC calculation, doing the exact same thing. We have this curve, and we're comparing it to our measured levels, but everything works the opposite way, sort of. Because for IIC, we're measuring how loud it is down below. So the quieter it is, the better. So we want lower ISPL or impact sound pressure level values. So we start shifting the curve down and we see how low we can get that curve before the deficiencies hit these different criteria. And we have two criteria for our deficiencies. So one is we look at the sum of all of those deficiencies. So the total of all those little orange bars down there at the bottom. And that can't exceed 32. We also look at the value of each one of those individual bars. And no single deficiency can exceed 8. And so we have some situations where the total deficiencies is what sets our rating. We hit that, we exceed 32 first, and so we go to that sets our level. And sometimes that 8 dB limit for a single frequency, that sets our rating. And that 8 dB limitation we call the 8 dB rule. And that's something that there's a lot of conversation about these days, and it's a topic for another day. So looking at these graphs, like if it's something that you're not familiar with, when I've presented this to other people that don't have backgrounds in acoustics or in music, looking at that, trying to understand the difference between all these different frequencies and how they sort of all occur at the same time is often sort of complicated for people. And so one thing I've found that has been helpful for people is this is a spectrogram. And right now, if you look at this, this might just seem super complicated. You're like, how is this helpful, Mike? This just confuses me more. The thing is to go to that link down there at the bottom, the amacoustics.com/tools/analyzer, and it's a live spectrogram that you can just play around with on your computer. And so if you spend a little bit of time with this, just get your microphone and start making some weird sounds into it, you'll start to understand a little bit better what's going on. So at the top of this, we have a keyboard. Again, to the left is lower frequencies, and to the right is higher frequencies. So you can think about this as sort of like the x-axis, that horizontal axis on those graphs I just showed you. And down below, we have color code. So this thing shows you the sound levels relative to frequency in time. And red is super loud, black is very quiet. And if you play around with this, you make different sounds, you'll see how they show up at different frequencies. And some sounds will have a very narrow frequency range. You'll see just colors in a little area, and other ones will have a much broader frequency range. And you can play around with different things, like make all the different vowel sounds and see the different frequency content of those. And this can really sort of start you help to understand, and it's a very visual thing, right? Hopefully it helps you understand sort of the different frequency content of different sounds. Bang on your desk, whistle, hum, do vowel sounds, all of these things, and you'll start to see that. So here I have a couple examples. I think this one was just like me, like clicking my fingernails on my desk or something. So it's fairly narrow and it's more high frequency content. And this was maybe pounding my fists on the desk, something like that. So it's much more low frequency, maybe a broader frequency range as well. All right, so now let's get into the shortcomings of the STC rating. So the STC is really designed around speech specifically, and it has a limited frequency range in part because of that. And if we think about the environments that we exist in, where we use STC ratings a lot, apartments, multifamily, condos, those kinds of things is a big one. So speech is certainly an issue there, but also like music, things from people's TVs and stereos and all of that. And that can cover a much broader frequency range than what speech does. So here is one of those graphs again, and it shows you the frequency range that's used in the STC calculation. So it goes from 125 hertz at the low end to 4,000 hertz at the high end. But here's the theoretical range of human hearing, which goes from 20 to 20,000 hertz, right? So here's the STC range. Here's the full range of human hearing. Now, the 20,000 hertz is way, way, way up there, and you lose that high frequency hearing as you age and you listen to music that's too loud. So probably most of us can't hear that high. That doesn't affect things too much. But those low frequencies, you can have, a standard sound bar that can go well below 125 hertz. And if you have a little bit of a home theater system with a subwoofer, it can go down well below 125 hertz. But we don't look at that for the STC rating. And the single number doesn't really tell the whole story, right? It's not looking at this entire frequency range, but it's also not telling us about the shape of that curve necessarily. We do this sort of curve fit that I went into where we compare that gray line to the orange line, but it doesn't when we just see an STC rating, like this wall is an STC 52, it doesn't tell us like, was it controlled by the total deficiencies or was it just like really bad at this one frequency? It doesn't tell us that. We have to go look at this graph to get that information. And again, going back to that quote at the very beginning, the code minimum does not guarantee satisfaction. Like if we're building condominiums and people are expecting high levels of sound isolation between spaces, especially if you have a place where, you know, people are maybe they're downsizing from a single family residence and they're moving into condominiums, they still bring with them that expectation of the sound isolation and the quiet that they had in a single family residence. Well, a condo building is a totally different environment. And the code minimum is not going to give you anywhere near that sort of quiet solitude that you had from a single family residence. All right, so now let's look at the IIC rating, so the impact insulation class. So it's designed around footsteps, and it too has a limited frequency range. So here's the range for the IIC calculation. It goes from 100 hertz to 3,150 hertz on the high end. But again, here's the range of human hearing. And just like with STC, the high frequency stuff, you know, we're not as sensitive to it, way up there. Some, you know, probably just can't hear it at all. It's really that low frequency stuff, though, is the thumps and thuds that you hear, especially in lightweight, you know, joist and truss structures. And those can often be the most annoying and disturbing sounds. So again, the single number doesn't tell the whole story. Same sort of thing that we talked about with the STC rating. And again, code minimum does not guarantee satisfaction. And that is even more so the case for the IIC rating than it is for the STC rating, I think. And to give you an example of that, here's a story. This is a paper in the Journal of the Acoustical Society of America back from 1994. And this is a big study that was done that sort of came about because of a class action lawsuit. It was a large luxury condominium building in San Francisco. There was an $80 million class action lawsuit filed against the developers. And one of the big claims in that was annoyance from excessive noise and vibration due to footsteps. And the complaints came from areas with and without carpet. So one of the things that we think about when we look at just like IIC ratings, for instance, any assembly tested with, you know, like broadloom carpet and pad, you know, for this typical residential carpet, usually gets these really high IIC ratings. And we think, okay, we've got this IIC 75 or whatever for this carpet. We're good. That's way above the code minimum of 50. That should be sufficient, right? But here in this case, the complaints were coming from places without carpet, hard surface flooring, that, you know, to be expected, but also places with carpet. And really what was driving that was the thuds and the thumps and the booming. That was the biggest source of the complaints. And you can still get that with carpet. And I think this is a very interesting quote from this paper. It says the IIC rating of a floor system is meaningless with respect to the perception of these low frequency, the thumps and thuds and booms, these low frequency components of footfall noise, because the methodology ignores the frequency spectrum below 100 hertz. Right, I just showed you that graph, and it goes from 100 hertz to 3,150 hertz. But we can hear things well below 100 hertz, and those sounds are important. So one of the things is you can get the same IIC rating for assemblies that behave and therefore sound totally differently. So here on the left, I have the same graph, right? We have frequency on the horizontal axis and the impact sound pressure level, how loud it is, on the y-axis, the vertical axis. So the higher it is up on the graph, the louder it is. All of the different colored lines represent the measured sound levels from one specific assembly. So we had that assembly in the lab, banged on it on top, measured how loud it was down below at this full frequency range, and then we get that graph, right? So each colored line is a different assembly. All of these assemblies have the same IIC rating. But you can see their levels at different frequencies vary all over the place. So here's the IIC range that's used for the IIC rating from 100 to 3,150 hertz. And so at the low end of that range, at 100 hertz, our minimum was 52 and our max was 65. So a 13 dB difference between the loudest and the quietest at 100 hertz. And for reference, a 10 dB change is a doubling in perceived loudness. So at 100 hertz, the loudest assembly here was more than twice as loud as the quietest. On the other end, the highest frequency, 3,150 hertz, the minimum was 5 dB and the maximum was 45 dB. That's a 40 dB difference. That's a huge, huge difference, right? So we have these massive changes in these assemblies and their frequency content, but they all have the exact same IIC rating. So if we looked at these assemblies just in terms of their IIC rating, we say they're all equivalent. But if you actually were to stand beneath one while somebody walked around on it or you had the tapping machine, they would sound totally different. So to address some of these shortcomings, we have two new standards that have been developed, the HIIC and the LIIC. So these deal with impact sound, right? Structure-borne sound. The HIIC stands for the High Frequency Impact Insulation class. The standard is ASTM E3222, and it deals really with the sort of the clicks and the clacks of impacts, footsteps on a floor. And it just looks at the range from 400 hertz to 3,150 hertz. So you can think of this as like the click of high heel shoes, or like hard soled dress shoes, or a dog's nails on a tile floor, those kinds of things. The LIIC is at the other end. It stands for Low Frequency Impact Insulation class. It's set by ASTM standard E3207, and it deals with the thumps and the thuds that were the big issue in that lawsuit. And it just looks at the frequency range from 50 hertz to 80 hertz. And so if you look at this, you see that orange bar, right? That orange line is the standard frequency range for an IIC rating. So you can see that the HIIC frequency range fits within what we already use for an IIC rating. But the LIIC is outside of that. It goes lower down. And that addresses that issue that Blazier and Dupree said in their standard, or their paper, that the IIC ratings are meaningless for these low frequency thumps and thuds because they just stop at 100 hertz. They don't go low enough to account for all that low frequency sound that is a big part of what we perceive. So the HIIC is easily measured as part of an IIC test because it's within that same frequency range. And therefore, it's also easily calculated from previously measured IIC test data. And I've done this at PAC. I've gone back to all of our 20 years of acoustical testing for floor ceiling assemblies. And I've taken that data and I've calculated an HIIC rating from it, because the HIIC rating is just a calculation standard. It's not a measurement test standard. And the HIIC rating is very useful for evaluating flooring and underlayments. Usually when we add flooring and underlayment to an assembly, the changes that we see in the impact sound levels are at these higher frequency ranges, really this range from 400 to 3,150 hertz. And that's why that range was selected. So we can use the HIIC to better differentiate between different flooring and underlayment combinations. It also works for evaluating ceiling isolators, so sound isolation on the other side of the assembly. The LIAC is a little different and a little more troublesome. So can't always be calculated from previous IIC test data because it's outside that range of frequencies that are measured for an IIC rating. And a lot of times the data that's reported and what the labs will measure stops just at 100 hertz. They don't go lower than what's required for the measurement of an IIC rating. LIAC ratings are rarely affected by flooring and underlayment. Carpet and pad would be an exception to that. Of course, there are some exceptions to this that I'm sure folks on here could point out. But generally speaking, flooring and underlayment don't do much for the low frequency impact sound. So the LIAC isn't particularly helpful for evaluating flooring and underlayment, but it can be very helpful for evaluating ceiling isolators and other changes to assemblies as well. LIAC ratings are hard to measure, or harder to measure, because of their low frequency range. And because of that, they have lower accuracy and precision in terms of their measurements. And there's unknown and at this point probably fairly low correlation between labs. So what that means is if you take this assembly and you measure it at this lab, and then you build that exact same assembly in this other lab, you might get pretty different LIAC ratings. There's also probably unknown and probably low correlation between lab and field measurements. So if you get this sort of a LIAC rating in the lab and you go measure that same sort of assembly built in the field, there might be big variations between it. And there's a lot of things that go into that. I'm not going to get into all of that, but just know if you see LIAC ratings, you got to take them with a serious grain of salt. And that's not to say that they aren't useful. The most useful way, the most helpful way for LIAC ratings right now is to compare tests that were done at the same lab. And so that's something that I've tried to do with our data is, test different variations of an assembly, maybe different sealing isolators, things like that, at the same lab, in the same test setup, so that you can see those changes in the LIAC ratings, and those are helpful, and those can be good design tools to figure out how to improve LIAC ratings in whatever assembly you're working on. And speaking of improving, let's get into methods of improvement. So flooring and underlayments, right? This is a common way that we look to try and improve impact sound, right? So in this case, I have this example of an 18-inch open web truss. It's got 3/4-inch gypsum concrete on it and a resilient channel for the sealing isolation. And so you go from a bare gypsum concrete to flooring and underlayment on it. And you can see that the IIC rating goes up significantly from 43 to 55. The HIIC goes up even more, right? That's that bigger differentiation between flooring and underlayments. So it goes from a 41 to a 63. So you get a big 22-point improvement. The STC rating goes down a point, but that's really within test variability. Flooring and underlayments really don't affect your STC ratings. And the LIAC rating went down 3 points. That's maybe a significant change, but like I said, there's less precision to those low frequency measurements. And so you might see some changes down there with flooring and underlayment, but you're probably not going to see too much. So sealing isolators is another way that we look to improve acoustical performance, right? So in this case, we've got the same base assembly, and the only change is that the assembly on the bottom, we've added some additional rubber isolators to the resilient channel to improve the isolation that's provided at the ceiling. And so you can see here, the STC rating went up, but only by a point, so really negligible change there. But the IIC, the HIIC, and the LIAC ratings all went up by significant amounts. And just a note, especially for the acoustical consultants on here, the STC ratings, this comparison is limited because of flanking limitations at the lab. Believe it or not, even as we start to get up to just STC 60, we start running into contributions from laboratory flanking. Another way that we can improve the performance of an assembly is adding mass. We do this a lot when we add additional layers of gypsum board to a wall, for instance, to improve our STC ratings, or we go from 1 to 2 layers of gypsum board on a ceiling. But you can also see it here just, increasing the thickness of a concrete slab. And adding mass will typically improve all of these ratings. Your STC, your IIC, and your HIC and LIAC ratings. Insulation is another way that we can improve our acoustical performance, right? If we have a wall with no insulation in it, that cavity between those two hard surfaces, right, becomes sort of this reverberant space. Sound can build up in there. And if we put insulation in there, it can reduce that buildup of sound and improve the sound transmission loss through the assembly. Same thing works for floor ceiling assemblies. And so you can see here by adding insulation to this assembly, the first one has no insulation, and the second one has 3.5 inches of bad insulation stuck to the bottom of the subfloor. We get improvements in all of our ratings. Now, something to look out for here is like, okay, well, if a little bit of insulation is good, why not put more insulation in there? Why not fill the entire cavity? That can improve your acoustical performance, although like with a lot of things with acoustics, once you've made one step in including an element, increasing that, so like increasing the thickness of your insulation, you get sort of incremental gains in performance, not just like this big gain. But the other thing to look out for is a lot of the places where we're looking at acoustics, we're looking at sound isolation between spaces like apartments and condominiums. We have acoustical requirements, but we also have requirements for fire ratings, right? That's very important. And a lot of times our designs for fire are dictated by UL fire-rated, fire-resistive designs, right? And a lot of those say that if you increase the insulation thickness above 3.5 inches, you have to change your channel spacing and you have to reduce your channel spacing. So increasing the insulation thickness might improve your acoustics, but you have to reduce your channel spacing, which might reduce your acoustical performance. Or if you forget to change your channel spacing, you may have an assembly that's actually no longer fire rated, and that would be a very bad situation. Two other things that you can do to improve the acoustical performance of an assembly are stiffness and damping. And I don't have examples of those because they're things that can just be a little bit harder to test in the lab. So, but stiffness would be, there's a project that we were involved in, a condo project, where it was steel C-section joists, and for whatever reason or reasons, the joists that were installed were under-designed for the span. And so the assembly was very flexible, and they were getting a lot of complaints about noise. There are other reasons besides just the stiffness that were causing the noise issues, but that was part of it. So they went back in and actually sistered in additional joists to stiffen the assembly. So you can, looking at the stiffness of assemblies can be a way that you can improve your acoustical performance or improve the benefits that you get from acoustical isolators. Damping is another way. So damping is sort of resistance to motion. And if we think about a car, right, as we're driving down the road, the springs in our car are the isolators, right? They help the wheels and tires move independently from the rest of the car. So the wheels take the bump, but we don't feel it inside the car. Damping is the shocks, right? So if we just have a spring, and you've probably all seen somebody driving down the road that has blown shocks or something, and they go over a bump and the car just keeps going up and down and up and down, right? That's because the springs have no resistance to that movement, right? So they'll just keep going back and forth oscillating. The shocks provide damping, so resistance to that motion. And we can add damping to structures in different ways. There's damped gypsum board panels, and there's other ways of adding damping. And there's probably some folks on here that get into really crazy tune mass damper systems for, high rises and things like that. So that can be a complicated subject, but just know that it's there as a tool sometimes. So in conclusion, code requirements, just baseline, right? Within the building code for multifamily sort of spaces, STC and IIC 50. And there are, of course, acoustical requirements for lots of other spaces. For hospitals and schools and office buildings, there's either acoustical requirements that might be a regulatory requirement that you're obligated to meet, or there may just be recommendations and guidelines. STC and IIC ratings have their limitations, and sometimes those limitations can be significant, especially with IIC ratings, and in large part, the exclusion of those lower frequencies that really better indicate the thumps and thuds that are often the most annoying and obtrusive sounds. HIIC and LIAC address some of those, and they can be good design tools when we're trying to select assemblies that perform well so we can make quieter spaces. Ceiling isolation can improve both your HIIC and your LIAC ratings. The code requirements are minimums. If you're designing condominiums or luxury apartments or something like that, places where people are going to have higher expectations for the level of sound isolation, you should be aiming for something above the code minimums. And again, with the current level of performance specified by the building code, a large percentage of people are highly annoyed by noises from the neighbors, leading to reduced quality of life and possibly the negative health effects. And really, the health effects of noise are significant. It's a big thing. There's a big body of research about it. Fortunately, a lot of it is done in Europe and outside of the United States of America, but it's really something to pay attention to. And I think that noise control and quiet are big parts of creating, healthy environments, healthy spaces within the built environment. And with that, I will turn it over to questions. So I think somewhere in here, I don't know if I have actually a way to allow everybody to talk, but Taylor, if you're here, maybe you can do that as the organizer. So if anybody has questions, you can raise a hand, and then I can try to unmute you, or you can type something in the chat as well. And again, for those of you who maybe weren't here at the beginning, if you are an architect and you're looking for AIA credit, you should go and make sure that you register through AEC daily and put in your AIA member number in there. That's how we'll get all of those things. And so we've got somebody saying they can't see any changes in the STC and IIC graphics. And then somebody else says they've had issues with connection. Is it possible to get a copy of the recording? So this presentation is actually, maybe the original version of this is on our YouTube channel. You can find it all on our website, and I will just grab a link and stick that in here as well. And it looks like Taylor says you should all be unmuted. So if anybody wants to you can unmute your own mic now, and you can just jump in and ask a question if you'd like.
So do you have a recommendation for what you should design your through higher and lower level measurements to be?
Oh, recommendations for the LIAC and HIIC?
Yes.
Oh, that's a great question. So for HIIC, I think the standard follows the typical guidelines that people will use for IIC ratings. So for STC and IIC ratings, if you go back and you look at that ICC document that I referenced, and I'll see if I can find a link and stick it in here. They say, code minimum is 50, sort of a level above that is 55, and the preferred would be 60. And a lot of times acoustical consultants will say, if we're doing, sort of affordable housing, student housing, something like that, we'll maybe design to that code minimum just because, price costs are really a driving factor there. If we're doing market rate apartments or something, we'll do a 55. And if we're doing, luxury apartments or condominiums, we'll do a 60. So that would be sort of the steps for an IIC rating. And I believe that the HIIC ratings sort of follow those steps. The LIAC, because it's this more nebulous thing in terms of how we measure it and all of that, and there's you can't just go back and look at old tests and calculate LIAC ratings. It's harder to go back to studies and figure it out. There's not yet quite like exact steps for what those LIAC ratings should be. That's something we're still kind of trying to figure out within the industry.
So with what you said, the LIAC is not very useful unless you can pick a number.
Yeah, it's so it's a standard that's been developed. I think initially intended more as a tool for acoustical engineers, consultants to help sort of differentiate between different assemblies and pick ones that perform better at those low frequencies. And it's not necessarily to the point of being like a code standard to say like, here's what the minimum should be or something like that. There's still more research that needs to be done in terms of, linking LIIC to actual perception and what hits specific, limiting annoyance and things like that from listeners.
So do you recommend HOAs set limits on both LIAC and HIIC?
HIIC for HOAs can be a really good tool because typically in an HOA situation, all you're able to change is the flooring and underlayment, right? You can't change the structure, and often you're not tearing out ceilings and changing your ceiling isolation. So HIIC is better at evaluating flooring and underlayments, which is usually the thing that people are changing in an HOA environment, right? And that's usually what the things come up about. So I think HIIC is a great tool there. LIIC is really going to be dictated more just by your structure and factors that often aren't in your control at that point. And I think I heard Norrell's voice
Yes.
piping in. Norrell, what have you got to say?
I can chime in a couple of things on that LIIC and HIIC.
Yes, please do.
Those were developed by the consulting firm of Benaclausen out in California. And they've done some rather extensive research. They do have some criteria and recommendations on the LIIC as to, at least in terms of a field measurement, if you measure something in the field, they've got some guidance on what is usually acceptable and unacceptable and so forth. I do not recall those numbers off the top of my head. The HIIC is not as far along in terms of having specific recommendations. the HIIC's greatest use is that in many cases, when you test a high-performing system, you can test several high-performing systems, and you might get about the same IIC. There's not much difference in the IIC ratings.
Mm-hmm.
You find those IIC ratings are being controlled by the sound in the 100 to 400 hertz region.
Yep.
All the high-frequency sounds been killed more so. But in perception, what people perceive mostly, what the Venaklazan people at least have concluded is that people primarily in footstep sound, they perceive the high frequency sound above 400 hertz, and they perceive the very low frequency sound, and that range of 100 to 400 is really not all that important. But that's what winds up controlling the IIC.
Yep.
So if you can get the data and look at the HIIC, you can often find that two assemblies that look similar in IIC really have a big difference in the HIIC, and that will be something that people will perceive.
Mm-hmm. Yeah, thanks, Noel. And there's a paper by the folks at Venaklazan, by John Laverty, Waylon Dong, and Samantha Rawlings in the Journal of the Acoustical Society of America and JASSA that goes into these HIIC and LIAC ratings. That was part of the sort of introduction for the research behind it to support it becoming ASTM standards. And in that is one of the places where they set out sort of their ideas of what the LIAC and HIIC criteria might be, and sort of some of that. So that's something that I can post on PAC's website, post on our LinkedIn and things to find links to those other resources so that you'll have them. I see somebody's got
the ASA paper is copyrighted, so it might not be easily found by people who are not members of ASA. So
yeah, I mean, you could find it and you could purchase it individually, and they're not too expensive. Jim, I see you've got a hand up. Go ahead and unmute.
Yes, looks like my computer is unmuting. Can you hear me now?
Yeah, I can hear you just fine.
Okay, great. So I've had a pair of projects, condominiums in an existing building where there was a total remodel and the ceilings were rebuilt with better ceiling isolation hangers and multiple layers of drywall, damping compound, and so forth and so on. The requirements of these projects were such that the new owners of these condominium units were willing to do what I suggested, which was to do everything that seems like it would work, for an effective result. And this was the existing floor system are TJI, the I-joist, wood I-joists, and I recommended that blocking be installed at third points of the span. Now, I don't have any before and after measurements on these particular units. I don't have any test information, of course, and I wonder if anyone has a gut reaction to the possible utility or perhaps, complete non-utility of stiffening a floor system of this type with, sort of ordinary spans. I think these were probably 24-foot spans.
Yeah, Jim, I don't know if I've seen any good papers like on before and after measurements or something like that. I know that Marshall Long mentions it in his book. Like he talks about that sort of blocking, and maybe that's where you got it, or maybe he got it from you. I don't know. But I don't think in there, because I've gone back and looked at that, and I don't think in there he actually presents like sort of before and after test data or something like that either. I don't know. I would love to see it. It's something that I've thought about trying. Maybe there's somebody else on here who's seen it or done it.
This is Noel Stewart. I can contribute 1 point here, at least. In the case of open web trusses, the Truss Joist Institute, which governs the requirements on those, requires that you have what they call I'm going blank now. What happens when you get 75 years old? a brace. They've got a name for it.
Bridging?
What'd you say?
Bridging?
It's not bridging. There's another name that's
Okay.
used particularly when you're cross bracing between trusses.
Oh, yes.
But they require that every 10 feet. In
Yep.
other words, if your truss is more than 10 feet, you're required to have one. If it's more than 20, you're required to have two.
Interesting.
Okay? And that's a part of the truss requirements. Then the truss companies will usually specify that. Oh, I wish I could think of that name. But it's the idea of running perpendicular to the trusses, tying them together with 2x6 typically. And they recommend tying together at least 3 trusses in a group. If you have to leave sometimes you might have to leave a space between some to run ducts or something, but try to tie together at least 3 together, I think, a minimum, and more when possible. Strong back, that's the name. Strong back.
Strong back, yeah.
So what they call a strong back.
So,
Between the trusses.
so Norrell, are these 2x6s placed flat on top of the lower member?
They're typically stood up. There's typically stood up vertically.
I see.
And against, typically your truss will have some vertical elements in it. They'll put it against one of those vertical elements and fasten it to that.
Yes.
Okay? And that gives you more stiffness and so forth. But it's a strong back. And if you do some searching on that, you'll find that the truss companies require that. Now, what I typically do is I like more than one every 10 feet. I like them more like every 8 or 9 feet. Especially on long spans when you get over 18 feet or so.
Yeah. Have you done any comparative
I don't have any
tests?
Data. Don't have any test data. It's just trying to be a little conservative there.
Yeah, maybe maybe that's something we can look into. I'm hoping to get to team up and do some testing with Evelyn at Maxon's new lab and to test some of our.
I think the problem with lab test, Mike, is that the problem is most commonly there when you have these long spans, longer than the labs can test.
Yep. Yeah, because then
just dealing with a 12-foot span, I don't think you're going to see much difference.
Yeah, no,
when you have
I
a 20, 25-foot span that you start seeing the difference.
Yeah, and I mean, I think that that's a serious limitation, one of many, with our lab testing, is that the spans that we're looking at are not at all indicative of what we see in the field.
Right.
So we in Phoenix were taking a fully all metal building where they had metal trusses and we did some measurements that built the building, and it was $4 or $5 million condo apartments. And it had significant noise and vibration issues, and we had to go in and make measurements and then get data. And by blocking and that helped solve the problem. So we do have some data if someone actually needs a little bit of data. So we've done some of that. But when you get into all metal buildings with all metal joists and all metal everything, where everybody wants to have openings to run all their HVAC through all these different places, it gets really complex. And the long spans are really a problem.
Yeah, and while I'm at it, I would be remiss if I didn't mention our assembly selectors. So I mean, I know a lot of you are familiar with this, but many of you may not be. So on our website, you can see here the registration link. We have these assembly selectors where you can go in and you can filter through different things. You can look for open web trusses, steel C-section joists, these kinds of things, and filter out this database of acoustical test results that we have. And so you can go in and access all of that sort of information. It requires a registration, just email, name, the basic stuff, and then you can get access to it anytime. And we do have some testing in here on, lots of testing on open web trusses. we have some stuff on steel C-section joists that came from that project I mentioned where it was under-designed and the structure was too flexible. And so you can see one of them there with the spring isolators, that first assembly. So that can be a good reference. But yeah, there's certainly, and I've tried to do things in here where, you know, I change a single variable as we do these testing so that you can see the effects on HIIC and LIAC and all of these ratings. But as we've been talking here, there's certain things that you just can't really adequately evaluate in the lab because of the limitations of the lab tests, like stiffness.
Yeah, so I think that it may be an interesting opportunity with the resilient clip systems for ceilings, in that they create a modestly deep cavity below the trusses. In Colorado, mostly what I see are these TJI wood trusses, and it looks to me that there could be a way, instead of trying to use lumber blocking or bridging between individual trusses, there may be a way to use steel C-channels on the underside of the truss, and therefore connect the trusses just the way Norrell is talking about strung backs with the open web trusses. And my understanding is of Long's entry in his textbook is that the purpose of those blocking, bridging, strong backs, and so forth is to reduce the twisting of the joists as they're loaded, and it transfers the load among several adjacent joists. So if you took you know, 1.5 inch by 3/4 inch the 12 gauge C channel and screwed it to the bottom of a bunch of joists, of these TJI type joists, I think that might be one way of approaching this stiffening issue.
Yes.
Yeah, that's
by eliminating the twisting, you make it stiffer. The twisting is more flexible. So.
Yeah, and you're transferring load from one joist to another. I'm surprised he hasn't chimed in here already, but Elzo is on here, and the one thing I would caution on that, or I'm just curious about, is within the UL fire ratings, you know, a lot of times, you know, the ceiling attachment methods are dictated within those UL designs, and usually it's resilient channel or it's some sort of clip and hat channel system like the RISC One or, you know, our other products. And I haven't come across any where, you know, you've got other sort of methods. Sometimes you can use drywall grid and things, but that's usually much bigger drops. So I like the idea for stiffening and also with I-joists, you know, you would have this path for moving things through. But I don't know about the fire ratings. And I see Elzo's got a hand now. Elzo, please chime in.
Well, thank you, Mike. Yeah, UL publishes the minimum requirement, and in conversations recently with UL, I have received clarification that they do not object to building the assemblies better. The key is knowing what's better. Stiffening the assembly, controlling the backside flange or the bottom flange, in their knowledge, is making the assembly better. And transferring the load from one joist to another is always a good idea, but at minimum, stabilizing that backside flange, as Mike and Norrell pointed out, is really, really the single most important thing you can do for long spans. And we see that not only C-sections, but TJIs and open web trusses. Keeping that bottom flange directly plumb in vertical plane with the top flange gives the man-made structural member the maximum strength possible. So you guys are all on the right path.
Thank you.
I'm curious if there are any architects or any others on here that have any questions. either of me or also of the other acoustical consultants that are on here too. I mean, if you're hearing from this conversation, we've got some folks that have a lot of deep knowledge and many years in the acoustics world, and far more so than I do also. So yeah, if anybody has any other questions, you've got an interesting audience here to ask them of.
Hey, Mike, it's Adam at Longman in New York. Question just in general about this conversation. I mean, we're all talking about, kind of in vague terms about making these structures more stiff, but is there any data about natural frequency and like, what's the typical natural frequency of a lab structure? And then, what's the range of natural frequencies that we're using in the lab tests? And then, of course, when you go to longer spans in real life, what we're talking about, where you start to see issues, and then when we're adding stiffening across joists, like, what is that? What are we creating? It seems to me that that's kind of the driving factor, and we should be talking to structural engineers.
Yeah, I think that's a great point, Adam. I mean, typically, looking at the natural frequencies of the structures is not something that we have, or that we do, that I've done, or that I've seen other folks do when going in and doing testing. And looking at both the natural frequency of the structure, but also the boundary conditions is something that I've been looking at and have played with a little bit in the lab, and how that affects the panel resonance, right? Because if you have fixed versus free boundary conditions, your panel modes change, and so that can change the response and also change sort of those resonant frequencies of your assembly. And that's stuff that isn't accounted for in the standards, and isn't necessarily, doesn't accompany test reports or anything like that. But it's all stuff that really does affect the performance of these assemblies, both in the lab and in the field.
Adam, Stewart, I would just chime in to say I agree with you that I think you're on the right track with natural frequency. I've long felt there was probably a optimum natural frequency for a floor ceiling assembly, but I've never been able to explore and figure out with any confidence what it would be. And I'd have some concern about it. I think the Blazier pointed this out some. I'd have some concern if it got too stiff. I don't know, we got danger of that, but that you could start raising your frequency up to where the ear is more sensitive and so forth. But it's a trick we play there in trying to deal with this footstep sound. The stiffer you make it, the lower your amplitude, but the more sensitive your ear. So
right, but also theoretically, generally speaking, the easier it is to isolate. So your isolators might be more effective at those frequencies, and it would be easier to get the improvements in sound isolation that you're looking for.
So this is Jim Borsman, Boulder, Colorado again. I have one piece of relevant experience with this question of resonant frequency. I was working on a building, industrial building, with some office spaces where there was a very high energy machine on the ground floor that was causing so much vibration in the structure that people could not read their computer monitors. And there were a couple of steps in this particular project, but at one point I asked the structural engineer if he could compute the resonant frequency of the floor slab system. And I'm pretty sure he used the Steel Joist Institute manuals, I think it's volume 11 or chapter 11, which gives a computational method. And the structural engineer came back with his computation. I had measured a resonant frequency of 6 hertz, and he said, well, the computation says 5.96 hertz. So I think that was a pretty good confirmation of the Steel Joist Institute methodology.
Yeah. That is
experience there reminded me of an experience one time. I had a project where there was a gym put on a second floor of a building, and they had the treadmills and rowing machines and so forth. And on the third, they were on the second, third, call it the fourth floor. there was an engineering office with computer monitors and a lot of things sort of out on arms and so forth. And those rowing machines and such down 2 floors below were shaking the building enough that they were having trouble reading their monitors and so forth.
Yeah, I've had stuff with treadmills. Like when I was at eCore, there was a project that came through where they had chandeliers in a big lobby area or something like that underneath the gym, and the chandeliers were like shaking, and light bulbs were breaking because of the vibrations from the treadmills. Actually, Nora, I may have even sent that project to you. I can't remember.
I remember hearing of the project. I don't remember whether I worked on it, but I remember hearing of a project like that.
I think you were one of the people, because I think it was over in your neck of the woods, at least generally. I think you were one of the people that I sent it to. There was something else that I thought of, but I forgot. Oh, so somebody, Victor, in here, I don't know if you're still here, in the chat said, what about edge conditions, i.e. floors and walls? Victor, if you're still here, you want to chime in? If you've got a microphone, otherwise you can just put any follow-up questions in the chat.
Hi, yeah, I'm here. Yeah, I was wondering, because we always look at these assemblies for the floors by themselves and the walls by themselves, but it would seem to me that one of the weak spots would be the transition between the two.
Yep. Yeah, and I mean, that's sort of the difference between, just very broadly speaking, the difference between laboratory and field measurements. And one of the reasons why generally when you go in the field, you don't get the same levels of sound isolation. And that's really where, the acoustical consultants like Noel and Jim come in, is, not just looking at the details of the assembly itself, but how it fits within the greater structure and addressing all of those details. And there's a lot of different ways that you can do them. But also some things can affect, all flanking paths and things like that too. I mean, like if you have an isolated ceiling, any sound that gets into that structure up above is going to be reduced by that ceiling isolation. Or if you have, isolation on your floor, acoustical underlayment or floating floor or whatever it may be, that can reduce the amount of sound that gets into the structure and then therefore goes to the space directly below, but also to adjacent spaces and things like that. But there's also a lot of things about looking at different junction details and all of that. And that's an area, like many others, where in the United States, I think we're behind some of the other countries. In Canada, the National Research Council of Canada has a test lab where they not only measure the direct transmission, but they also measure all these different flanking paths. And their code, I think, actually requires calculation of those sort of junction, transmission losses and those different flanking paths. And in Europe, there's also more requirements and more research going on in that. So other jurisdictions are addressing that. But in the United States, we're really sort of just, at least from a code standpoint, just looking at the direct transmission. And Jim or Norrell or anybody else on here want to add anything to that?
Well, I would like to ask two questions. The first is pertaining to edge conditions. We all know that the best practice is to create what I call a resilient isolation joint at the perimeter of ceilings. Now that can be created by making a physical gap, or it can be created by using certain kinds of products. In your opinion, your professional opinion, do you think that detail is very helpful, slightly helpful, or immaterial?
In terms of that isolation detail at the edge of the ceiling,
Yeah,
having the isolation there rather than, are you asking like having the isolation there versus having it rigidly mounted, or
Yes.
just how it's the type of isolation that's there?
No, whether it's there or not.
I think it's definitely important. We have some testing, I think it's in the database, on a concrete slab with different ceilings hung below. maybe it was the ADM. I can't remember if it's in there, like if we have full test reports for it or not. But we've done some prior to my tenure here with isolated ceilings where they used L metal at the perimeters, because that's pretty typical with drywall grid or something like that. And those tests don't get the level of isolation that I would expect based on some of our other testing that I've done. And I think it's because of that transmission at the L metal. But it also like can be hard to test in the lab depending on the frame for your opening and what other transmission paths are there and how you're addressing those too. Elzo says we have some backed by riverbank tests. Elzo, do you know which specific tests where you may have looked at those edge conditions?
Yes, Mike, when we were doing testing at Riverbank, we wanted to answer that question. And so we built a resilient rubber isolated ceiling and left a 1/4-inch gap, caulked it around the perimeter, ran the test, then removed the gypsum board, put 1.5 inch angle at the perimeter and retested, and we had a 7-point reduction in the IIC and similar reduction in the STC. So I would suggest the edge condition or the perimeter condition is critical, very important to the acoustical results.
Elzo, do you know, are those test ones that we have full test reports for that might be in the database? Or is that before I started making you pay for test reports for everything?
Yeah, it's when I was in my much cheaper mode, trying to get $2 worth of work out of every dollar. Those were data only. We did not publish an official report. All we did was learned that our original concept of totally isolated ceilings and totally isolated walls we thought were important. We verified it was important. And for us, we were satisfied with the results. And now in retrospect, I apologize to everybody for not doing the whole job. And with that, I'll mute myself. Thank you.
Well, so sounds like I've got some more tests to run.
So that was really useful information. Thank you for that. Thank you very much.
Also, everyone, I would say that that 7 points in a laboratory might not translate to that much difference in the field.
Yep.
Because in the field, you're going to have some flanking coming down the walls anyway.
Mm-hmm.
That are going to be adding in there. Yes, it makes a difference what you're doing when you isolate the ceiling. You're eliminating that flanking part getting back into the ceiling and radiating from there.
Yep.
And in the laboratory, that's all you got.
Yeah.
But in the field, you're going to have some in the walls also that's going to be significant. So not quite as much difference in the field as what you see in the laboratory.
But still not a reason to not do it.
Yeah. Now, one of the issues that comes up when you do that, isolating the ceiling, people want to know, well, what do I make that look like? How does that look? And so forth. And ideal situation is you put some kind of molding up there that covers the gap and so forth, but doesn't attach the ceiling and the wall.
Right.
The crown molding attached to the wall only, with a slight gap above it and so forth. But if they don't want to do, a lot of places don't want to do the crown molding, they don't want to leave an unsightly gap. I have, through the grapevine and years of talking to people and everything, found and understand that if you do mud and tape it, as long as you leave the gap there and caulk it, you can potentially get by with mudding and taping and not have a great problem, except for the potential problem of that tape cracking sometime, because it is flexible and you don't expect it not to crack necessarily.
Yeah, that's been my practice also.
Yeah,
So,
I think NRC did some measurements where they looked at adding mud and tape or just using mud and tape as the seal, and from an acoustical standpoint, it didn't seem to diminish the performance or anything like that.
You don't want the gypsum directly in contact. You don't want the two pieces of gypsum directly contacting.
Correct. You need a gap, and the sealant needs to be something that's going to stay flexible.
Right.
It's not going to harden and become rigid. And there are specifically acoustical sealants, and there are fire-rated acoustical sealants that you can use in those, and you need to make sure that you're using one that's approved for the specific assembly that you're using it in and the way that you're using it, because some are different for walls versus ceilings, because gravity works more on the ceiling, and so there's some nuances there to pay attention to.
So here's my second question. There is a manufacturer whose name shall not be mentioned here that makes fiberglass pads that can be used to make a resilient connection between wall bottom tracks and head tracks from adjacent structure. Does PAC have a product that can be used in that same manner?
Yes, we do. So we have a couple different options. So we have a fiberglass pad that you can use to isolate the base of the wall, and then we have rubber isolators that would go on the fiberglass pad would go underneath your bottom plate, right? And then we have rubber isolators to isolate the screws on the top side. So we have that. It's our HIIC WFI, right? Wall frame isolator. We also have our HIIC U, which actually I can pull these things up because I have the internet and share them. So our HIIC U, we have a version that you can use again at the bottom to isolate the bottom plate, and then we also have one to isolate the top plate, which is our HIIC U HD. That's the head of wall, and that is included in several fire rated like head of wall details. So we have a couple different options for you in those those areas.
Well, Mike, yeah, I'd love to get that information from you, and also your recommendations for mounting televisions into hotel guest room walls.
Yes. Mike? Yes.
Mike, Chips.
Hey, Chips, how are you doing?
Well, I'm doing well. One of the things that seems to be missing here that I've ran into with a very famous actor, where his wife always wore high heels going from the living room in that area back to the bedroom through a hallway. He had new slate floors put in and everything, and beautiful baseboards and all of that. And when they were the contractor put in on cork, but the guy down below ended up with 4 attorneys in this lawsuit that was going on. And what they did is they pinned the baseboards back to the floor. And they wouldn't let me test anything. I took a screwdriver with me and I tapped the back end on the floor, and I had somebody else do that. And I went downstairs, and you could put your ear on the wall up on the hallway and just tap it lightly, and it went right into the wall and just spread down below. They pinned the baseboards. They had to go back, pick up all the baseboards, put them in, and leave a gap on them.
Yep.
And that solved the problem.
And that's more important than the ceiling, in my opinion.
I mean, yeah, I couldn't believe how much transfer in the living room, where it was a wide dissipation of energy going out. It was not much problem at all. The hallway was the major problem.
Yeah, because it gets right into the structure, right down those walls of the hallway that are right next to your ear. You get flanking issues like that. They always show up more in hallways and bathrooms and small rooms than in a large room.
Yeah. The one caveat there is that when you put a gap under the bottom of a baseboard in a restaurant, it needs to be a sanitary sealant in there.
You have to caulk it.
Yeah, you have to caulk it, and
it must be caulked.
Yeah. So I want to chime in with a couple other things. So one, Jim from Sonic CSD in the chat added, floor system resonances play a big part in determining the annoyance factors below, something that we've been talking about. In general, adding mass and stiffness play a big part in lowering the transmission of forced vibration sources. This could be from gym equipment, sub-bass speakers, or even walking strides. In general, adding spring isolation is many times a valid remedy. HIIC SIX is a good solution to help with this condition. So that would be our one of our sort of low profile spring isolators. So thanks for that, Jim. And Mike with MD Acoustics agreed. Mike was one of the ones that worked on that project with the C-section steel joist I mentioned earlier. And our RIIC SI1 Ultra spring isolators were the solution for that particular project. And actually, some of the test data from that one, Ben Schaefer and I will be presenting on at NoiseCon in Kentucky next month. So here's the SIX. And there was also a question in here from Frank Lotto. Frank, I don't know if you're still here. I apologize if I got your pronunciation of your last name incorrect. Says, I use the INSOL program to run testing info on wall and floor ceiling systems for our building designs. Is this an adequate program for an architect to use, or is there something better? So yeah, I have my thoughts on that, and I'm sure others here have their thoughts as well. So first thing I would say is another resource that you could use for trying to find those. Like, I prefer laboratory test data over INSOL, but there's issues with laboratory test data as well, right? And sometimes INSOL can kind of help you figure things out. Like, none of them are perfect. So I would encourage you to go and register, if you haven't already, for access to our database so that you can get, you know, the acoustical test results from things that were actually tested in the laboratory. So you can use that sort of cross-check what you're getting in INSOL. It's a way to look into these different things. And, you know, INSOL can be a useful tool, but there's also a lot of times, like, I have INSOL and I use it some, and I'll put things into INSOL and it's not at all what makes sense to me or what I get in the lab. So, you know, if you want to kind of get an idea, like you just commented, of a system that you can't find test data for, and or like a change to a test assembly or an assembly that you can't find data for, you could get an idea of it, but I would definitely, you know, put some significant plus or minus values on whatever you get out of it and take it with a grain of salt.
So let me just explain. We use INSOL all the time in our acoustical evaluations, but what we find with INSOL is that we need to have our own data to put in there. You can't just pick from the data selector and know that you're getting anything reasonable. So we always have lab data that we validate with, and we've actually contacted the guys in New Zealand and have them work with us on developing models for our specific cases. And I would be a little bit suspect for an architect to know how to do all that stuff. It's hard enough for us as acoustical engineers focused totally on that I'd be a little bit nervous about just using INSOL by someone who doesn't know what's going on.
Yeah, there's a lot of different parameters that go into it, right? And if you change one of those parameters, if you get it wrong or off or something like that, and you don't know generally sort of in theory what that change is going to do to the assembly, you might go down a completely wrong direction and not know it. If you don't have some sort of other references from field tests that you've done or laboratory tests you've seen that you can use as a gut check to make sure what you're getting out of INSOL makes sense or doesn't make sense. So yeah, I mean, I would encourage architects to look to the manufacturers or, you know, other sort of industry references like the NRC reports or something like that to find things, and also just work with an acoustical consultant that does know all of that theory and the ins and outs of it to make sure that what's being built is a good design.
Thank you all. This is Frank. Thank you all for all the information. And yes, I use it only for, as we're in the planning stages, whether we need to fortify a system to reduce the sound or get it somewhere near where we want it. But I found, like, if I try to put in a deviation that it's not in the testing program already, trying to get the correct information from a manufacturer is like going to a dentist and having them pull all your teeth out. It is truly painful. Yeah, and I try and go with published information as much as possible. And right now I use that. And yeah, I do use the plus or minus. And I tell all the people in my office, like, yeah, I'm giving you a 54 to 57 because I have absolutely no idea exactly where it's going to fall, especially once they go in and build it. But thank you for the information. And yes, I am already part of your database.
Okay, great. Yeah, and I mean, one of the things that I'm trying to do is make that process of getting test data not as much like going to the dentist. Because I know, like, I was an acoustical consultant for 10 years. So I worked, doing what Jim and Noel and Mike and a lot of these other folks do for 10 years before I started working for manufacturers. And so I went through that same process of trying to get test data from manufacturers. And a lot of times, you're up against the deadline, you need to get something out, and, it's 5 o'clock on the West Coast, therefore it's 8 o'clock on the East Coast and nobody's there and stuff. So that's why I put together this database to be a resource to try and make that process easier. So you can just go get it, find what you want, mess around with it and stuff. But feel free to reach out to all of you. Reach out if you're looking for test data. You can't find it, the database isn't making sense, or you've looked through here and you can't find what you're looking for. We're trying, to keep doing more and more acoustical testing. So, come to us, right? It never hurts to ask. Certainly no guarantees. I'm not going to guarantee I'm going to get to spend Elzo's money on more testing, but I'll try if it makes sense for us. Let's see, are there any other questions in here, or anybody else? I mean, this has been a great discussion. I really appreciate everybody's input and everybody sticking around well past the end of this. I've had several people in the chat ask for if there's going to be a recording of this. Chips, I know you emailed me and said you had connection issues at some point. I think we are still recording this, and so we can go ahead and we can post this up on our YouTube channel. And figure out different ways. Maybe we'll break it up into 2 sections, one being the presentation and one being the discussion afterwards, because this discussion has been really great. So we'll post that, and we've got the email list of everybody who signed up, registered for this, so we can send you out an email with a link too. Any other questions before we sign off here and call it a day?
Thanks, Mike.
Yeah, thanks everybody. I really appreciate it. It's been a great discussion, and yeah, it's great to have all the acoustical consultant folks show up and adds to the discussion, because there's certainly a lot of very knowledgeable folks here, folks more knowledgeable and more experienced than I am. So it's great to have y'all add to this conversation. So yeah, with that, thank you very much, everybody. I hope you have a great day and a great weekend. And we will do another one of these. I'm not sure what we're doing next month, but look for us to post. Next month won't be an AIA accredited one. It'll be some other sort of informational webinar. But we will be doing the AIA accredited ones, I think, once a quarter or something like that. So if you have other folks that might be interested, feel free to let them know. We'll post about it once we get it scheduled.